at New River Air Station in North Carolina. Marine Corps Squadron 266, aka the Fighting Griffins, are preparing to undertake a training mission.
Got radio, sidewinder. Yeah, looks like you're ready to rock and roll, sir.
Designed to test their ability to overcome the challenges of modern military operations.
In today's battlefield, it's constantly changing. We never know what operating environment we're going to have to confront, whether that's the desert, urban environments, or Arctic weather. Confronting America's adversaries, we need to be able to understand, decide, and act. Our ability to do that quickly and act quickly with adaptability and flexibility will be key to our success.
And when it's time for the Marines to enter the action, they can call on an aircraft that's capable of the ultimate adaptation. This is the V22 Osprey, a revolutionary feat of aviation engineering that combines the speed and range of an airplane with the land-anywhere ability of a helicopter. It's a multi-mission powerhouse that allows the US military to achieve the seemingly impossible.
This aircraft, in my opinion, defines the 21st century Marine Corps.
The Osprey is truly impressive. When I look at it, I'm blown away by the technology and the capability it's able to produce.
The MV22 can fly as high as 25,000 feet and hit 280 knots. We can carry 12,500 pounds externally and has a range in the ballpark of 750 to 800 nautical miles.
Nothing can compare to the Osprey. It's one of a kind, and I love it.
Equipped with a pair of 38-foot rotors, the Osprey can take off vertically like a helicopter, pivot its blades forward, and transform into a propeller-powered aeroplane. Capable of carrying 24 fully loaded combat Marines and slinging the equivalent weight of an African elephant beneath the fuselage. It's the ideal aircraft for flying troops and cargo into seemingly impossible-to-reach locations. For Marine Colonel John Spade, the Osprey is an invaluable tool that's helped redefine how his team can operate.
Our ambition as Marines was to be able to project power well forward. The V22 Osprey was created to achieve and accomplish that ambition. This aircraft is giving us the capability we've never had before by combining both an airplane mode and a helicopter mode, which allows us to quickly respond to emerging situations that are in front of the Marine Corps right now.
And this game-changing machine is pushing the boundaries of what's possible for America's armed forces.
Unlike any other aircraft, we can take off vertically, transition airplane mode, get to great distances at great speed, and land vertically again. This allows us to get in those austere locations quickly and with great response.
Engineers have built an aircraft with a unique ability. But how do you design a vehicle that can transform from helicopter to aeroplane whilst in flight?
The capabilities of a fixed-wing aircraft and the capabilities of a helicopter are completely different. Combining those capabilities into a single airframe is particularly difficult.
How do you keep the aircraft under control while it shapeshifts in mid-air?
You have centers of gravity shifting, you're operating at different speeds, so the characteristics of this aircraft are constantly changing.
And how do you stow a giant aircraft into the cramped confines on board transport ships?
So we have to be able to fit a high number of V-22s onto our amphibious shipping, so it's important that we can fold it and fit it into tight spaces.
The V22 Osprey is one of the most remarkable machines on the planet. Built to carry troops and cargo at high speed over long distances and into hard-to-reach locations. It can achieve the seemingly impossible by transforming itself from helicopter to aeroplane in mid-air. Operated by a crew of 4 Marines, the Osprey is powered by a pair of Rolls-Royce engines that can propel it up to 500 kilometers per hour. A top speed more than 50% greater than the planet's fastest helicopter.
All right, NGMP, NR are stable above 75. Ready to start 2. Start 2. Copy, no choose, come start.
At New River Air Station in North Carolina,
We are stable above 20, kill 3. Roger, kill 3.
266 Squadron are making their final preparations before taking to the skies on a training flight.
Please check this reviewed, complete.
But in order to make today's exercise possible, it requires some of the most groundbreaking aviation engineering that's ever been put into action. A feat that never fails to amaze Osprey engineer Rod Olson.
The Osprey is designed to take off like a helicopter and fly like a fixed-wing aircraft. It then lands like a helicopter as well. The capabilities of a fixed-wing aircraft and the capabilities of a helicopter are completely different. Combining those capabilities into a single airframe is particularly difficult because you have to balance design requirements in order to achieve an optimum solution. The mechanics and physics involved in solving the transition between helicopter mode and airplane mode are particularly complex.
In order to solve this problem, engineers can look to history's innovators for answers. Helicopters versus propeller planes is one of the oldest debates in aviation history. With a helicopter, you can take off vertically and land without a runway. But if you want to fly fast, climb to high altitude, or travel long distances, a propeller plane will always win. At the National Museum of the US Air Force in Dayton, Ohio, aerospace engineer Lynn Pickering has traveled to see a game-changing experimental aircraft.
Oh my gosh! Look at this thing! Looks like it's straight out of a sci-fi film. This is the Bell XV3. It's the only one left of its kind. I would have to say this is one of the most exciting pieces of aviation engineering that I've ever seen.
Making its maiden flight in 1955, the XV3 is a truly pioneering flying machine. Developed as part of a joint research program between the United States Air Force and Army. The experimental engineering introduced on the XV3 laid the foundations that helped make the Osprey possible.
This aircraft is actually the first attempt at tiltrotor technology. And so what that means is that this is in helicopter formation now, but when the aircraft takes off, these blades rotate down into airplane mode. And then when the aircraft needs to land again, they rotate back up, lands like a helicopter.
These cleverly designed rotor blades allowed for a previously unprecedented mid-air switch.
This is wild. You'd think that something like this should be impossible, that you take off like a helicopter and then you transform kind of like a transformer and then you're flying like an airplane. So it's always been a bit of a holy grail for aviation engineers.
Leading the quest to realize this ambition were Bell designers Bob Licton and Kenneth Wernicke.
I just think of how daunting this must have been to design something like this. When you're trying to combine those two concepts into one airframe, you run into a lot of issues.
And during a test flight in 1956, the XV3 would demonstrate just how difficult it is to perfect tilt-rotor technology. After the aircraft suffered extreme vibrations in mid-air, the pilot passed out, causing the prototype to crash, forcing engineers back to the drawing board to reassess the XV3's design.
So the problem that the XV3 was running into was something known as mechanical resonance, which I'm going to try to explain with this short demonstration here. Basically, I've got a pendulum. It's just made out of a string and a tennis ball. And it, just like all other objects in the natural world, has a natural frequency, a frequency that it likes to vibrate or oscillate at. And if I push it at a frequency that's too high, it's not going to do much, right? It's just going to stay right here. And the same thing happens if I push it too slow. Not much is going to happen. It's just going to swing back down. Now, if I match the natural frequency of the pendulum, see what happens. It'll get faster and faster. It's going to spin out of control, which is exactly what happened with the XV3. If you imagine the string and the pendulum as the wings of the aircraft, and my force as the vibrations created by the rotor, you can see what went wrong. The force of the rotors matched with the natural frequency of the wings and caused the aircraft to vibrate out of control.
Having realized the flaw in their design, Bell's engineers set out to find a solution that could solve the resonance problem.
So if we look at the wings, we can actually see one of the key design changes after that first crash. They've added these struts in here to make these wings a lot stronger, and that changed the whole frequency of the structure so that it no longer is going to resonate with this tilt rotor tilting down. And let me show you another aspect of the design change. They actually changed from a 3-blade design up here to 2 blades. And they strengthened and shortened this pylon here on both sides to make this stronger and decrease the vibrations. And then inside this fairing here, we've actually got the electrical motor that completes this 90-degree arc in only 10 to 15 seconds. So very quickly, you're able to go from helicopter mode to prop plane mode.
After incorporating the new design elements, the XV3 successfully overcame its problems, completing more than 100 full conversions of its tilt rotors between 1958 and 1962. Making it the first aircraft to achieve a feat engineers had long dreamt of.
The XV3 might just be one of the most important pieces of aviation engineering. It really took this concept of combining these two technologies, which a lot of people thought was going to be impossible, and they proved that it was possible.
Takeoff runway 23. Got a request an airplane departure.
On board the Osprey,
Runway 23, vector left turnout for Osprey point departure. Roger.
today's flight crew are about to embark on their mission. Just like on the XV3, the Osprey uses its rotors in the upright position to take off vertically. Then pivots them forward through 90 degrees, allowing the wings to generate lift, completing this seemingly impossible conversion to propel a plane in a little over 12 seconds. As Osprey engineer Rod Olson knows, the secrets behind this incredible tilt-rotor technology are hidden inside the structures on the aircraft's wingtips, known as nacelles.
So contained within the nacelle, there are several components that allow it to operate. Primarily the engines, which are in this lower portion. Then there are gearboxes further up, drivetrains, and ultimately the rotor system here at the tip. The pylon conversion actuator is responsible for actually moving the nacelles up and down. It has dual redundancy, so in the event of a failure, the pylon conversion actuator can actually allow the aircraft to land safely.
The pylon conversion actuator is a hydraulically powered telescopic ball screw. As the screw is rotated, it extends and rotates a lug that is coupled to the nacelle, causing it to pivot from the vertical to horizontal orientation. When the screw is rotated in the opposite direction, the nacelle returns to the vertical orientation.
If you look at the nacelle and the tilt rotor, you can see just how impressive the engineering is that went into this. The tilt rotor technology employed on the Osprey is unique. It is not used anywhere else in the world in an operational status.
Remarkably, all it takes for Osprey pilots like Major Thomas Cecil to carry out this incredible transformation is the push of a single switch.
The V22 makes the transition from helicopter mode to airplane mode with really just the flick of the thumb. On our TCL down here, we have a nacelle thumb wheel, and all we have to do is push forward on the thumb wheel and it begins to actuate the nacelles forward towards airplane mode. So when I push forward on the nacelle thumb wheel, it's going to actuate conversion actuators on either wingtip, and through the conversion actuators, it'll modulate the nacelles down. When we're ready to convert again and come back to VTOL, it's just a reverse process. We'll pull back on the nacelle thumb wheel as we revert back to typical helicopter-style controls.
It's a groundbreaking achievement that's only possible thanks to the Osprey's innovative aviation ancestors.
The technology demonstrated by the V22 is really a long time coming and the result of multiple decades of engineering. And it all starts and is all built off other aircrafts.
There's one military aircraft with an ability that's totally unmatched. The V22 Osprey. This incredible half-plane, half-helicopter hybrid is amongst the most impressive machines available to the US Marine Corps. Equipped with a pair of transformational tilt rotors, the Osprey can convert between flight modes in just 12 seconds, allowing it to take off, hover, and land like a helicopter, and fly at high speed and altitude like an airplane. In the skies above North Carolina,
200 feet, gear 3 down, locked.
266 Squadron are underway on a training exercise designed to simulate the challenges of real-world operations.
Copy, 80 feet, all calls in the back. Roger, clear right.
With the Marines regularly deployed into the planet's most challenging terrain, it's essential that the Osprey can get them there safely.
Dust building.
And that means being able to land in conditions where visibility is almost non-existent.
And brakes, heel, to the deck.
Major Thomas Cecil is one of a select breed of elite pilots who understands the demands of flying the Osprey.
We have to be able to take this aircraft into any environment, and because of the amount of downwash that we create, we have to be ready for dust, sand, snow, anything, and that's going to reduce our visibility when coming into land. Losing visibility during landing is extremely dangerous. If you can imagine pulling into your driveway with your eyes closed while you're driving your car. Do you just trust yourself to just stop before you crash into your garage door? But in this case, we have maybe up to 25, 27 people's lives on the line and very expensive equipment. If we were to crash an aircraft, that right there is mission failure. So it's very important that we're able to take off and land in a reduced visibility environment.
Incredibly, engineers have designed a solution that allows the Osprey to operate in zero visibility and help pilots avoid disaster.
We have a couple different ways that we can do this. One is through an automated approach, which is pre-built into our flight plan to assist the pilot to make a safe landing. We're really talking about the very final stages before landing, and this is where we're going to lose our visibility outside.
By using GPS technology to identify a suitable landing location, the Osprey can control its drift and rate of descent to safely touch down without any input from the pilot. And the aircraft's high-tech instrumentation can also be used to automate a landing when loss of visibility is not expected.
We can also use automation on the fly, and we engage that utilizing the flight director panel. For the primary piece that we're looking at here is the hover coupler, and utilizing this is going to give us varying degrees of lateral control assistance to minimize drift. It's also going to help us slow the aircraft down and give us a controlled rate of descent. When we're ready to land, we can disengage basically the altitude control, and then we control the altitude and rate of descent.
It's an amazing solution that's essential to allow the Osprey to land in the world's most hostile locations in zero visibility.
It's just not possible without this system and without these displays that we have.
But having built such a capable aircraft, engineers now face the problem of how to keep it stable while it morphs in mid-air.
There's a lot of challenges with operating in conversion mode. In order to land, we have to slow down. This involves converting. And as we do this, changes the configuration of the aircraft and brings some different handling characteristics into play.
To help keep the Osprey stable through this unique conversion process, engineers can look to the pioneers of the past. Engineer Dan Dickrell has travelled to the heart of Georgia.
Oh, I can't wait to see this. This is gonna be awesome.
To discover a plane with a trailblazing design.
Dang, look at that. What a beautiful and shiny aircraft. It's a Lockheed Electra 12. It's a classic example of Art Deco era of aviation. There's only about 10 of these left in the world, and today I get to fly one.
First taking flight in 1936, the Lockheed Model 12 Electra Jr. is a pioneer of passenger aviation.
7 Lakes traffic, Lockheed departing runway 18, 7 Lakes.
Building on the success of the Model 10 that went into production 2 years earlier, the Electra family of aircraft were famed for their forward-thinking all-metal construction and early adoption of twin engines.
All right, you ready to go?
Yeah, man, let's go flying. Oh, this is awesome. Man, what a pretty view. That was one of the smoothest takeoffs I've ever experienced, even in a small plane. Maybe it's a testament to how cool this airplane is or the skill of the pilot, but whatever. Like, that was definitely a top ride experience that I've ever had.
And as Dan's about to discover, the Electra is an aircraft that's remarkably easy to handle.
All right, so you ready to fly?
I am. Thank you, sir.
Airplane's yours.
All right, I have control of the airplane. Oh!
But in the early days of the Electra's development, a flaw was found in one of its key components that threatened to keep it grounded.
When it comes to aircraft control, one of the primary control surfaces is the rudder, the tail, and that's the part that allows the plane to yaw in the sky and go left and right. So much like the steering wheel in a car allows the car to turn left and right, I have two pedals on the floor that I have my feet on, and if I press the left rudder pedal in strongly, there we go, it turns to the left, and if I press my right pedal in. We go to the right a little bit. There we go. Those are the basics.
Initially designed with a single tail positioned in the center of the fuselage, wind tunnel tests showed the Electra was vulnerable to instability in flight.
This is obviously a problem, especially if you're trying to design a passenger plane. So the engineers knew that they had to solve this in order for this aircraft to be successful. All right, Glenn, you ready to take back over?
Yeah.
Right on. Thank you, man.
Remarkably, Clarence Kelly Johnson, a 23-year-old student working on the Electra program, proposed an answer.
So Johnson realized the problem with the prototype stability came down to the single tail. And his solution was this, a twin tail design. This is something that had never been seen on an aircraft at this point. And look at it, it's amazing. It's like a big shiny whale tail.
But this revolutionary design is not only easy on the eye, it also holds the key to solving the Electra's stability problems.
The reason why the twin tail works as well as it does comes down to placement. If you can see, the propeller on this side of the aircraft is almost in line with the tail, right? The reason why that helps is because the slipstream that's coming off of this propeller is in a position where it can interact with the control surface, this rudder. And remember, a rudder helps the airplane yaw left or right in the air. In situations where there's low speed, either on takeoff or landing, the ability of this control surface to safely move the airplane around is most important. And that's one of the upsides of this design versus a single tail. Single tail can't take advantage of that alignment and that increased airflow. And so that's why this twin tail works as well as it does. Additionally, since there's two tails, there's twice the area, you have much more control authority to maneuver this plane in the air. It's a brilliant solution.
Not only did Johnson's innovation dramatically improve the Electra's in-flight stability, it went on to become a signature of other Lockheed aircraft.
Nice.
And more than 80 years on from its introduction, the iconic twin-tail design has had an enormous influence on flying machines of all shapes and sizes.
So not only is the Electra one of the most beautiful airplane ever to take to the skies, but it's a real pioneer and an incredible piece of engineering.
Over 85 years since Johnson introduced the twin tail on the Electra, the Osprey's pilots can call on the same innovative concept.
The twin tail is what gives this aircraft that directional stability when we're operating in airplane mode. On each vertical stabilizer, it has a rudder. Those rudders are both actuated utilizing the pedals on the floor of the cockpit, and we use that to control and make directional control inputs. Also in between our two vertical stabilizers, we have the horizontal stabilizer with the elevator, which is this giant kind of whale tail, which you see, and that gives us longitudinal control.
As with the Electra, the Osprey's use of this tail technology is key for ensuring a smooth flight experience.
We have to have a certain amount of stability. Without the twin tails, this aircraft would be much, much harder to fly.
And this stabilizing innovation is also involved in steadying the aircraft through its challenging conversion process.
The twin tail makes it possible for this aircraft to transition between airplane and VTOL. When we're in airplane, all of our controls are actuated similar to any other airplane. And then as we move towards VTOL, everything is made through the similar control inputs to what you would see with a helicopter. In between, it's a combination of the two.
And converting to helicopter mode.
So as we transition from airplane type control inputs towards helicopter type control inputs, It's a blend, utilizing the tail, whether it be the elevator, the rudders, combined with inputs through the prop rotors to achieve for the overall output and control that we require.
It's a brilliantly modern use of this historic technology that helps give the Osprey its one-of-a-kind capabilities. To transport troops and cargo anywhere in the world,
2 is setting up. Roger.
engineers have created a shape-shifting military flying machine. Part helicopter and part airplane. The V22 Osprey is the ultimate aircraft. Fitted with 3 fuel tanks in the fuselage and more integrated in the wings, the Osprey can hold around 6,500 litres of fuel. That's about 85 times more than a family car. And enough to fly non-stop from Miami to Philadelphia. In the skies above North Carolina,
Tail right to land on the Delta taxiway.
the 266 Squadron flight crew are returning to New River Air Station, having completed a successful training flight.
Firm 3 down and lock. Just so you know, I got Blackburn on top radio, I got Blackburn. Copy. All right, come to 80 feet. Tower clear, right? One's on deck.
But, as Major Thomas Cecil understands, in order for the Osprey to carry out its worldwide missions, it must be able to travel distances far beyond its flying range.
So the Marine Corps, as our nation's force in readiness, it's important that we have an aircraft that can operate in any place around the globe. So it's extremely important that the V-22 be able to fit and operate off of existing amphibious shipping. We have to be able to fit a high number of V-22s onto our amphibious shipping that has limited hangar space. So it's important that we can fit it into tight spaces.
And as engineer Rod Olson knows, squeezing an aircraft with an 84-foot wingspan into a restricted footprint presents a potentially impossible problem.
The size constraints the Osprey has to fit in are approximately 20 feet wide by 20 feet tall by about 63 feet long. It's a significant design challenge to combine all of the details of the Osprey into the small footprint while still meeting critical flight characteristics.
To find a solution, engineers must seek inspiration from the pioneers of the past. In San Diego, in the US state of California.
Oh my gosh, this place is absolutely massive.
Helicopter pilot Mika Muzio is on board an iconic aircraft carrier, the USS Midway.
It's incredible to be standing here. This is 4 acres of floating aviation history. Can you imagine what this was like back when active? The sound of the jets, the spinning of the blades, all that activity.
Commissioned in 1945, the Midway was once the largest ship in the world.
As an aviation nerd, it's cool to see all the aircraft, but putting them in the context of an actual aircraft carrier really brings it to life.
But with wings and blades that span huge distances, and hangar space limited on even the largest carriers. Efficiently stowing each aircraft and maximizing carrying capacity has long posed a problem for the Navy. Thankfully, in 1943, engineer Michael Boyvid helped design a helicopter equipped with an ingenious solution that would redefine how aircraft are transported.
Look at this thing. It's amazing.
This is the Sikorsky H-5, also known as the Dragonfly.
From a pilot's perspective, when I look at the cockpit, I just think the field of view is incredible. You can just see in all directions.
Capable of operating from a variety of US Navy ships, the H-5's versatile design was an instant success.
So the H-5 was special because it very high performance, flew up to 21,000 feet, which is something I've never done in a helicopter. What's amazing to me is how much still is relevant today. There are so many components on here that just worked, and we've stuck with them. It's remarkable.
Built to offer the armed forces a helicopter that could carry greater loads and fly longer, faster, and higher than had previously been possible. The H-5's impressive performance allowed it to become the first helicopter to operate in the Antarctic. But arguably the most important of this exceptional aircraft's features were its revolutionary rotor blades.
Look at these blades. They take up so much space. It's like a big ring all the way around the helicopter. That's really inefficient use of space, especially if you have the confines of an aircraft carrier. We're in a hangar right here. There's not a lot of space. The rotor system, it's roughly 50 feet in diameter, and if you get two of these side by side, that's 100 feet of space that you're taking up just because of the rotor size.
But as Mika is about to discover, with help from the carrier's crew, these blades have a trick up their sleeve to help solve the problem.
So the first thing you're taking out, that's the pitch link bolt.
The pitch link, it
Gotcha.
controls the pitch of the blade.
Okay.
Now what I'm gonna do, I'm gonna rotate it, so basically I'm gonna change the pitch on the blade.
Okay, we're going down.
Going down, now he's gonna pull the wing or the blade attach bolt out so that we can swing the blade.
Gotcha, and that lets the whole blade rotate back.
Yes.
Okay. Here's the moment where I hope not to drop it. Okay. Oh, and it just rotates back like that. Okay. That seems pretty easy. Okay, just walking it back. Okay.
By removing just 2 bolts, the blades are ready to fold, allowing the H-5 to be totally transformed in little over a minute.
Okay, coming down a little bit.
So we're gonna drop the blade down.
Okay, drops down.
Slide it up into the cradle.
Slide it up. And then 2 bolts back here for the little clamp, and it's good to go. When they started bringing the H-5 onto ships, they would just fold them back like this, and this is how you'd store them.
Yeah, except for back then, you had 2 20-year-old sailors doing it.
So a couple of old guys like us.
And by repeating the same process on the opposite side of the aircraft, the H-5 can complete a feat that had previously been impossible for a helicopter, fully folding its blades and shrinking its footprint significantly.
All right, now what I'm gonna do is I'm gonna rotate it a little farther to where I can drop it out.
And coming down a little bit. Okay. I'm not gonna say there's a lot of pressure here, but this is a very old helicopter, and the guy holding the blades, don't want to break it. Got that, there we are. It is remarkable, though, that just a few seconds ago, this thing was ready to fly.
Yes.
Well, ish. And now here we are. Okay. That was suspiciously easy. I think I'm ready to join the crew, guys. I'm ready to join your squad.
Boyvid's transformative blade fold design helped revolutionize the transport of military aircraft, dramatically reducing the space required to carry a helicopter.
What's incredible to me is that we've gone from 50 feet wide to 5 feet wide in about a minute.
And today, blade folding is still an essential feature on an array of modern aircraft, proving the importance of Boyvid's ingenious invention.
To me, this folding mechanism is a real game changer, making it possible to fly a helicopter from a shipborne environment. It's really incredible.
Today in North Carolina, the Osprey's engineers have taken Michael Boyvid's blade fold innovation and modernized it to achieve a pioneering first of their own.
This is the world's first complete blade fold and wing stow system. There are other platforms that use a portion of blade fold or a portion of blade stow, but in no cases is there a complete process all in one aircraft.
Unlike the manual fold method designed for the H5, the Osprey's unique system is entirely automated, a process that has to be seen to be believed.
At the start of the blade fold sequence, the swash plate actuators that control the rotor head move to the fully retracted position. This causes the blades to pitch vertical. The aircraft then folds the outer two blades so that they join the blade that's currently over the wing. Once that's complete, the nacelles begin to rotate down into the horizontal position, and in doing so, the wing also begins to rotate.
Once the wing has completed its rotation to sit parallel with the airframe, the operation is complete, taking approximately 90 seconds to shrink the Osprey from 84 feet wide to less than 19.
The execution of the blade fold wing stow is like a party trick. It's amazing to see such a massive aircraft turn into such a small footprint like this.
It's a truly remarkable transformation that's vital to allow this amazing machine to operate from the confines of an aircraft carrier.
The blade fold wing stow system is essential to the success of the Osprey.
The engineering behind this extraordinary aircraft has given it unmatched ability to take on missions that were previously impossible.
Every day I look at the Osprey, I can't believe how amazing it looks. The engineering that was involved to design this aircraft blows me away.
It's an extreme honor and privilege for me to be part of this Osprey team, not just for this fantastic aircraft, but also to work with those men and women that keep this aircraft flying.
By looking to the pioneers of the past for inspiration, adapting their ideas, building on their designs, and triumphing over enormous challenges.
This is a game-changing aircraft for the Marines. It accomplishes things that no other aircraft can accomplish. It's a real-life transformer.
The Osprey's team have created a revolutionary piece of aviation engineering and succeeded in making the impossible possible.
It wasn't long ago that people thought it impossible to combine both helicopter and airplane capabilities. We've redefined what's possible on the battlefield.